Okay, this is our verbal team of Sampson Community College, and this is ELC 111, November the 3rd, 2020. And today we're going to cover Chapter 9 in our textbook on voltage drop across conductors. Very important topic. It comes in, the importance of it has to do with whenever you have very long runs of wire. You know, when you're talking, 200, 300, 400 feet of wire, which can happen in plants and on farms especially, and you are hundreds of feet away from the power source, because of the resistance that's in the wire. We studied the resistance that can be in wire, that is in wire, in Chapter 8. And that resistance is very small, but when you come with hundreds of feet of wire, it becomes a factor that causes you to lose some of the voltage from the start to the end. You don't end up with the same voltage that you started with. And in general, the National Electric Code requires a general figure of 3%, no more than 3% voltage drop. So whatever you start with, if you end up with less than 3%, if you have more than the 3% loss, then it's not considered to be acceptable. It can be harmful to the equipment. Motors can be running on under voltage and they can actually overheat. It can damage equipment. So here in this chapter, you're going to see some different percentages allowed, because in some cases they actually have a tighter requirement than that 3%. So anyway, we're going to go ahead and start. And we are looking at the principles of voltage drop across conductors and the problem-solving techniques used to properly select your wires. Now, voltage drop can happen. It's a loss of the electrical potential or voltage in a conductor or wire due to the resistance that we know is built in there, Chapter 8. You can see the effects of voltage drop each time the lights may dim as a toaster is connected, or maybe if you're heating an air system, every time it kicks in, do y'all notice the lights flicker some? The microwave can do it. It's a heavy load that can actually produce a little dip in voltage momentarily in your house, so it can affect everything. Dimming, that symptom can be reduced if you go with larger conductors, larger wires. You have less effect like that. So the larger the conductor, the lower the resistance, and you have a higher current carrying capacity with bigger wires. But when you pick your wires, there's a compromise because of money. So it's a compromise between the cost and the allowed voltage drop. So basically what you do is you'll calculate based on the allowed voltage drop, so that you end up with the smallest wire you can use and stay within code. Now, if you wanted to calculate based on no voltage drop, you can certainly do that. But people have a tendency of just calculating based on what they're allowed to have in voltage drop. And then they save a little bit of money. They save some money because copper wire is pretty expensive. The resistance of your wire is based on that. We know that voltage equals the current times the resistance. So if you have a certain amount of current going through a wire, and then that wire has a certain amount of resistance to it itself, the current through it times the resistance of the wire actually tells you what that voltage drop would be. So that's one way to actually calculate that. It is a factor of the length and the area in circular mills, and the resistance is actually given per foot. You can, that's something that we're going to look at. It's actually on a chart. The chart tells you per 1,000 feet. The total resistance can be found by multiplying the total length by the per foot resistance that you can come up with off of a chart very, very easily. Now here, we have a circuit with a generator. The G is the generator, and you have 180 volts at the generator. And the way that they're describing this here is you have 584 feet of wire total. When they point up and down, they're actually referring to the round trip of the wire. So that's already been doubled up. If you see an arrow pointing this way, it's referring to a one-way distance, not the double. So that's one little thing that you have to watch closely in this chapter, is if the arrow points this way, it only represents the distance, and you got to double it if it's a 2-conductor single-phase circuit. Okay. So here you're starting out with 180 volts. You got a total round trip of 584 feet of wire. The motor requires 20 amps, and you can get that off of the nameplate of every motor. They all have a what you call a FLA rating of full load amps, and the full load amp rating is 20 amps on this motor. And they're showing you that you started out with 180 volts and you ended up with 176.4. And we're going to look at how did they come up with that. Okay, so if you look on page 76, the wire itself has a resistance. They're telling you 0.308 ohms per 1,000 feet. That's information that's given on page 76. So let's see if I can actually draw on the screen if I get it set just right. Let me get in that mode there where I can do that. Have to sort of get the screen set up just so to do this. Okay, now let's see, where is the, yeah, you can do drawing. Let's see. And then draw and then red. So it said that the resistance in the wire was 0.308. .308 ohms per 1,000 feet. That information actually came from, if you back up and look at let's take a look at you go back to chapter 8. So we're going to flip between chapter 8 and now what? So if we go back to 8, let me enlarge that some. 8 and 9, they go hand in hand. You can't separate them. They really go together. Very tight knit. Okay, so we're sitting here in chapter 8 on page 59. Okay, so here we go. The resistance per 1,000 feet, the 0.308. And what size wire is it? The actual AWG size. It's a number 4 AWG. So this is this is where that comes from, and that's a piece of information that we can go ahead and plug in to this. So we know it's a number 4. Okay, those are standards there. That's a set thing that come out of the code book. This is a very exact subject that we're talking about. It's a very exact thing. So now, So how do I calculate the resistance of, I know what it is for 1,000 feet. Now, how do I calculate it for 584 feet? What's the method of doing that? You want to break that down to 1 foot. What's the resistance for 1 foot? So it's 0.308 for 1,000 feet. And a simple step, how would I break it down and divide it for 1 foot? Right, you divide this number by 1,000. Just like you're seeing right here, you just simply say 0.308 divided by 1,000, and that equals what? Look, you basically move the decimal over 3 places. You've got to add 3 zeros, and you put in 308 per foot. So that's for 1 foot, and then you want to multiply. What do we do next? Times 584. And then that's going to give us the exact number of ohms of the wire, of that number of feet of wire. How much? And let's see how they round that down. They round it to 0.18 ohms. 0.18 ohms. And we know with Ohm's law, if we have with Ohm's law, back to that triangle, you have E, I, and R. Now the voltage drop, you can calculate the voltage drop how? Voltage drop would be E, right? It's a way of looking at it. So if you cover that up, what does it equal? It's I times R. So the I would be what? $20 amps times the R, which is what? The 0.18. 0.18 ohms. So it equals how many volts? 3.6 volts. So you lose 3.6 volts. Now let's see. Do the calculation. Is 180 minus 3.6? Does that equal what it says up there? Right, the 180 that you start with, that's the generator voltage. G's for generator. So that right there minus 3.6 is going to give you the 176.4. Changes the mode. Right, you subtract that, you say the 180 minus that, and it's going to give you that over there. Everybody cool with that? Very, very straightforward stuff. Very straightforward. Any questions? Okay, good. Next. You just circle it and tap it, and it erases. Pretty neat. the mode, you got to be in the right mode to do whatever you got to do. Okay, so our next okay, now this is our next scenario. If we're starting out with 257 volts on the generator, we have a distance of 250 feet. Now look, when they point the arrow that way, what does that mean? That's one way. So in your calculation, the length is going to be double that because there's two wires involved. So just keep that in mind. And it's telling you that you're starting out with 257 volts. The motor requires 50 amps. You use a number 4 copper wire. And they want to know what is the voltage at the motor. So you got to calculate the voltage drop and then calculate the result of that. This is the stuff that if you know this, you can be one of the few out there in the field that know it, that use it. And it can be, you can be a guy that installs equipment right on a farm or an industry or something like that. You can be on point the first time and be the hero, not the zero. Like as Ruben Casual used to say, that was one of his famous things. He said, don't you guys want to be the hero, not the zero? So that's how to do it. Because I heard of a farm that, I don't know what farm it was, but they bought a bunch of equipment from Miller Controls, a company I used to work for. They installed a whole house full of equipment like a hog house or whatever. They called Wayne one day. They said, Wayne, ain't none of that equipment you sold is running right. Ain't none of it working right. It's all over, the fans are turning slow. It's all moaning and groaning and nothing's working right. He said, okay. He went out there, took his voltmeter. He kind of knew what it was. That hog house or whatever it was way, way away from the highway. And they had low voltage at the building. The entire building was under low voltage drop. And it's because somebody didn't calculate they didn't do what you're getting ready to learn in here. So the result was the contractor had to pull a new wire from the highway to that house. Bad news. Bad news. So somebody had an embarrassing moment there. It's okay. I mean, you learn years ago. I learned this stuff once I got into studying electric code. When I was asked to get licensed, state license, then I got into the preparation for that and come across this stuff. So for a lot of years, I didn't know about this. I had an electronics degree, but we didn't study this stuff per se in electronics. So it was eye-opener for me. It's very important. So the method here that they're going by, there are two formulas we're going to look at, and you're going to be using one or the other. If you're calculating for voltage drop, then you use the formula on the left, VD, and then if you're calculating for circuit and mils or wire size, then you use the formula on the right. CM will be the circuit or mils of a particular piece of wire. So here's what you have here. If you have an installation, if you got a hog house that's say 400 feet away, 500, 600 feet away from the highway, if you know the distance, then you have L, right? Then I would be the current, the amps that's required for the entire house. You have to have a calculation for the entire building. And then the K factor, now here's something, listen real good here. This K does not mean 1,000. This is the one time in electrical that K does not mean 1,000. Here, K is a constant. It is a constant figure that goes back to chapter 8. You remember, K is the resistance of a mil foot of wire. 1 foot of wire, 1/1000th diameter is a mil foot. And they're telling you here, in this example, that K is going to be equal to 12.9 at a particular temperature. Let's see if we can get, reduce the size of this. I think we're missing something here. Yeah. So The K is a constant. It's going to be a fixed 12.9 ohms per foot at a particular temperature. All right, so current in amperes. Length is the total length, which would be distance there and back. If it's a two conductor, if it's single phase, you just double the distance. Now, when we get to three phase, which we're going to get to in this period here, three phase is not covered in the chapter, but we're going to cover it because you've got to have it. And I've added that in there, and it's a little slightly different figure here. CM is going to be your cross-sectional area in circular mills. So in this example, what are we looking for? You want to know the voltage drop at the motor, right? That's what you're looking for. So we are using, tell me how to set the formula up. Yeah, we're looking for, hey, we're solving for voltage drop. Get you some of those here, Jamie. Any of those that you don't have. That's a schedule, and you may not need that schedule over there, but or you may, you see, you won't go take any more classes.
I'm still waiting to find out if I'm in.
Yeah. If Ronnie knew.
Ronnie was leaving, but my boss man now, because I'm on call.
I understand. You may be better off this way.
Classes.
Yeah.
Like that.
You don't want to really be, you're kind of in a stress situation right now. You might better back off right now. Yeah. And just kind of don't give yourself high blood pressure. It ain't worth it. You know. You got a really good job, and you've been stepped up now from welder fabricator to field troubleshooting electrical technician. Yeah. You made a big step. He came out here and took, his boss knew that he had the ability to learn electrical. He was their main electrical fabricator at Broad Hoxlab. Main welding fabricator, I'm sorry. Yeah. And so they lost their main electrical guy, he just changed jobs. And so his boss saw me one day at the grist mill and said, "Look, I got a guy, Jamie Jones, and I want to turn him into a good electrical technician. And can you get him in your motor control class, like real quick?" And it was the last minute. The class was getting ready to start just in a day or two. Yeah. And it happened to be that me and Barney happened to be at the grist mill, and his boss, bam, he intersected perfect time. That's pretty interesting intersection right at that day there. It was like a divine appointment, it looked like to me. So anyway, he said, "Can you get him in?" I looked, and Barney happened to be sitting 2 seats down from the guy I work for over here. I said, "Barney," I said, "you think we can get him in?" We were already maxed out, and the numbers already over the limit. You were 21. He was number 21. That's right, I forgot, because it was the biggest class I've ever had. And I said, "Barney, you think we can get him in?" He said, "Yeah, I reckon we can." He said, "You think he can handle it?" I said, "Yeah, I can handle it." I said, "Ronnie, I believe what Ronnie tells his boss, Ronnie Goblin, if he wants to do something, it's worth doing." He said, "You want to get on board with Ronnie Goblin, whatever he's up to, because it's going to be a winner, whatever he's investing in, it's going to be a winner. He don't waste his time and money on nothing." So that it proved right, and I knew it that Jamie was going to do really good. So we're happy about that. But that automation class, if you wanted to get it at some point, it's a great one. So we're going to calculate that. So what's the formula we just learned about voltage drop? What is the formula? VD equals what? VD equals what? KIL over CM. And so K in this case is a fixed number, which is what? 12.9 ohms times, and then what's the current? I is the current, right? It's 50 amps. And then the length is going to be, well, if we have a distance of 250 feet, what's the total length of the wire? 500 feet. Jamie, the reason why we're doubling this is because, look, the arrow points in one direction. If it was up here, if that 250, if it was pointing at both wires, then they would refer to a round trip as already being doubled. The first problem in the chapter had the arrow pointing up and down the footage, and it referred to the round trip already. Now, if you go back to image on figure 9.1, it actually already had double there in figure 9.1. No, the K can change based on the temperature of the ambient temperature in the room. So if you notice, if you go back on page for this particular problem, it's 12.9. If you back up the chapter 8, you'll see K be something slightly different. You know, it can be. They're going to give you that K. That K is given every single time. It has to be given. It has to be given. You know, you never guess about K. You don't never guess about K. No. You go back up. Go back down. I've rotated back to chapter 8. You see here in chapter 8 it says that K happens to equal 10.4 ohms at 68 degrees Fahrenheit, but K also goes up to 12.6 at 167 degrees. We do know that the resistance of wire is dependent upon temperature. So if the hotter the room is, the copper has more ohms to it. It doesn't like it. It doesn't like the heat. So it's more resistant to current flow the hotter it gets. Okay? So that's, if you figure, what I've seen in general is most popular would be the 12.9 because that's like a worst case that I've ever seen. And that's what you see, the guy that I took code class from in Raleigh years ago, he just stuck with a flat 12.9 as best I remember. Because that would give you the worst case scenario. If you figure based on that, you'd be safe. Even though your environment may not be that hot, you're still best off being going with a worst case figure. Hey, Hunter. It is, yeah. They bring a mask. Make sure you guys have a mask on. You come right on into the shop classroom, and we'll register right in here. That's exactly right. You come into the shop in 146C in the classroom. That's where I'm at now. I'm teaching until then. Yep. Y'all come on. You and Bryson, yes sir. But make sure you got a mask on. We got to have the mask on, and we got the distance, about 6 feet at least, okay? 2's fine. Yep. That'll work. Okay. Bye-bye. That's fine. He's coming. Him and Bryson will come to the register.
So if I go ahead and sign up for that, I forgot what it's called.
ELC 215.
Yeah. If I'm going to sign up for that, is it going to affect you if I have to drop it?
No.
Well, I'd rather sign up for it and not be able to take it. Get to be able to take it, can't get it.
Right. It ain't a bit of trouble if you drop it. It's not, because I've already got 11 people in there already. It's already.
Trying to get out and let me take it, but I don't know.
But what you can do is, look, if you go in there and take some pictures, go in there and get a close snapshot of the panels and then an overall picture of the whole line, and just tell them that it's Allen Bradley PLC's Ethernet connected, it's Ethernet network. It's a step up from what you've been doing anything else. It's advanced PLC. The programs that are in there are way more advanced than what you did over the summertime.
When I was in maintenance, that's what I did with Billy Parker. We built all our own equipment. But that's exactly what he does. I helped him do a
Okay, yeah.
And I got to do the boss of the wrong now, so
Right. But if your farms are connected with Ethernet,
we don't work.
you don't work on that. You got a contract that does that. Okay. So I don't know whether you would.
So I got to get approved for him because we don't have set hours like I had at the point. You know what I mean? And they've been more one time where I've come to class at night time and somebody else has had to fill in the cover for me to come to class.
Yeah, gotcha. Okay. So now, what is CM? We got to divide by CM. We get CM, the information from, it's a number 4 copper wire. So if we go back to chapter 4, back to chapter 8. Let's go back to chapter 8, and we're going to look at a number 4 copper wire. So number 4. So if you go back to this chart here on in chapter 8, and a number 4 copper wire, let's go up where you can see the headings up top, and go back out some. You'll need the chart, yeah. I have to put that stuff in there. I'll have to put it in there, but you'll have to have all the formulas. I have to get all the formulas to you. And but you go ahead with your paper copies too, because the Chromebook is a small screen. So yeah, bring your formula sheets. I'll make sure that you've got the stuff in the exam that you need. It's going to be, it'll be, I'll have pictures in there with formulas and stuff. I'll make it as easy as possible. I've got my work cut out for me on this exam, if you believe that. But yeah.
Well, there's several fish places hinging on that.
it's hinging on that. Okay. I hear you, James. So, a number 4 copper wire, what is the circuit of Mills? 41,740. So you don't guess at this stuff. This is stuff you just got to know where to go get it at, bang, you plug it in, and it spits it out. This is a plug and play thing here, okay? So remember that number, 41,740. I like how it does that. 41. You're going to put that mode back. 41,740 circular meters. So you have resistance times amps times feet, total distance. You double the 250 over the circular mills, and then what do you end up with? What's the result? 7.73 volts, and that and what does that number represent? It's the voltage drop. So let me just tell you, and actually, this is actually in reality. Watch what I'm going to do here. You couldn't physically do this, but this would actually work if you could do it. Now watch closely what I'm going to show you here. This is for real. If I took this voltmeter, watch what I'm going to say here. Look closely here. We know that a voltmeter, if I put it on volts, we know that a voltmeter, the display tells you literally the difference in pressure or difference in voltage between 2 points. So, you know, if I were to go across here, it would say 257, right? Now, if I go out here, it's going to show me less than 257. It's going to be the 257 minus the 773, right? Which would be what? Let's go ahead and figure that. So 257 minus the 773 equals what?
$249.27.
249.27. 249.27 volts is what you would actually read at the motor. Now watch this. Very important. Very important. Watch really close. Don't miss this. If I go out here and I measure across the motor, I'm going to read what? What's the meter going to tell me? You just figured it. What is it? What's the meter going to tell you? Right here. Exactly. The meter's simply going to tell you 249.27. Now watch this. Seriously. If you could do this, this is what the meter would tell you. Watch. If I could take the voltmeter seriously and put the voltmeter here and put the voltmeter out yonder and measure the starting and the ending on each end of that wire, what would the meter say? If I could put one wire here and one wire at the end of it at the motor, if I could stretch it that length, but you can't because the wires ain't that long. But if you could, remember that the voltmeter tells you the difference in voltage between 2 points, always, the difference. So what's the difference between the starting and the ending point? If I've got the meter sitting on volts, and I'm actually going to read volts, but I'm checking voltage from the beginning to the end on that wire. What do you think the meter will say? Not zero, it can't be. Because look, what's the voltage up here? What is it over here? So, and look, so what's the difference between the two? Well, no, we're not talking resistance, we're talking voltage. We're talking volts now. We're on volts. Yeah, the resistance makes it drop, but I'm actually got the meter on voltage now. Yeah, it's that simple. I mean, the meter could tell you, listen, the meter would tell you 7.73, it would read the drop. It would actually read the drop on the meter. Yeah, that's what I'm trying to get you to realize that literally, you're losing 7.73 volts from here to here. That meter could tell you that if you could actually stretch it from beginning to end and put it on there, it would say 7.73 somewhere in that neighborhood. The meter would tell you what the drop is. But you can't physically measure it because the test leads are not that long. But it could be measured. And the way you can prove it is, listen, is you measure it here and you measure it there, and then you just have to subtract the numbers, and that proves what the difference is. Exactly. Yes, sir. Exactly, because of the resistance of the wire. Exactly. So if on your farms, if you start at the highway and measure, you go out to the higher house and measure, there's going to be some voltage drop. Guarantee you, you ain't going to get what you start with. You're never going to get that. On the line, a definite difference. There has to be because of the resistance in the wire. Yeah. Especially in your world, this is a big deal. I mean, a big deal. Sure is. Okay. So does that help any kind of seeing that if you could stretch that meter out, the meter would physically tell you, bam, it would tell you what it is, and it wouldn't lie either. Okay. So everybody cool with that? Any questions? keep in mind, we were solving for voltage drop. That's the formula. You can also have where you can use this formula, and it's going to just tell you the wire size that you need for applications. So if you want the formula to tell you automatically what size wire to use on a farm, you would use this one right here, Jamie. That one right there. And all we've done here, if you take a look, y'all take everybody looking, everybody watching, everybody with us, everybody watching here. Don't be on the phones. You're gonna lose out. Make sure that you're watching this stuff good. Yeah, pay attention good here. Here, KIL is at the top of both of those. Now look, if you switch VD and CM, if you flip them and switch those up over here and put CM on the outside and VD down there, that's all you're doing whenever you rearrange those formulas. So why would you ever use this one? This is the perfect one to use to take all the guesswork out of what wire size that you want to use. Let's say if I got a 500-foot run of wire, so many amps, and the VD, the way you come up with the VD is like this. Voltage drop in general by National Electric Code is 3%. That's your general number for a single branch circuit, okay? The 3%, what you can simply do, whatever voltage that you're running at, very simply, typically 3%. Let's say, for instance, if you're starting out with 240 volt, you figure 3% of 240 and you plug that into the formula, you put the K factor, the amps, and the length, and it's going to tell you directly the right size wire to use automatically with no guesswork. This is the one you want to use right here if you're installing stuff, because you take all the guesswork out. If you want to be tighter than 3%, you can say 1% of that, plug it in there, and it's going to kick you out the circuit of mills. And then you go to chapter 8, go down to the third column of circuit of mills and come back to the AWG. Bam, it's going to give you the wire size, and it'll be perfect every time. Guaranteed. It's going to be dead on. You won't never go wrong like that. Yes, sir. This is the one. This is the one that takes all the guesswork out of it, and you will not go wrong using that one. So Jamie, you need to share that one right there with you guys. Actually, both of these, if you know, the more direct approach is just simply using this one, and you're the one that's going to decide on the voltage drop allowed. Sure. Yeah, we're getting ready to. Yeah, we're getting ready to right now. Yeah. Absolutely. The very next example, in 9.3, it's going to put that in use. Determining conductor size. So this is exactly what you asked for here, James. It says that you have somebody read at the bottom of page 77 the information there about 9-3.
Shows the motor operating from a 220 volt DC source, drawing 50 amperes. At full load, a 2% drop in line voltage is permitted. Find the smallest size of conductor to use and then line 150.
Right, so it's 50 amps and 2% voltage drop. So let's put that information there in. So 50 amps, 2% VD. Okay, so let's use that formula then. What is the formula that gives us the direct wire size? The one we just looked at.
Yeah, the CM equals.
Right, CM equals.
KIL over VD.
Right, over VD. Okay, y'all talk to me. And let's see, what's our K factor going to be here? The most recent one said 12.9, right? And it's still 12.9 in this example. The K factor is, it's a constant per mil foot of wire. So the K is going to be 12.9 ohms times the current, which would be how many amps? 50 amps. And then the total length would be what? Well, it's a 100-foot distance, but the round trip is what? It's 200 feet. 200 feet. And then we got to come up with a permissible voltage drop. VD is going to be 2%. 2% of what? 2% of 220, which would be 220 volt times 0.02 is 2%. And what will that be? 4.4 volts. Don't round no numbers. Do not alter none of these numbers. Use exact numbers. Exact. Stay exact, because it can throw things off if you don't. So. On what part?
So it says find the smallest size of conductor to use in a line 100 foot.
Right.
Why are we figuring out 200 foot with Kevin? I see it's a round trip, but it's only asking for 100 foot. Why are we making two?
That's the distance. You have two conductors involved. You got two conductors involved. Yeah. No, it's actually two hots. But it can be a hot neutral. If it's 120 volt, you're still considered the same thing.
So if it was 120 volts, still would make it.
Because listen, look, watch. You've got current flowing this way and then back this way, right? And it's a total wire length of 200 feet. You have to figure that in there. And you see in the book, it has to be figured that way or it's not going to be right. Yeah. When we get to three phase, we're going to do three phase after in a little bit here. Three phase is a different calculation. You don't say times three, you say a different figure. It's a factor in there, square root of 3 goes into there. And you're going to see that it's different. And it has to be, the engineers give us that, and we just have to just take it on what they say. You can't have a circuit with one. It has to be a circuit would be a loop. All electric circuits have to have a loop like a circle. You can't have a circuit without a loop. It has to be a loop. It has to be a going out and coming back. With three phase, instead of you saying the length times 2, it's the length times 1.73, which is the square root of 3. And it has to do with using three hot wires that are that are 120 degrees out of phase with each other. I'll draw some three phases up here when we get that. It's different. It's a different animal.
So you coming off the panel part.
Yes, sir.
And you run into a plug that's going to run 2 or 3 different things. You need a 240 volt plug down there and it's 250 foot.
Mm-hmm.
So you plug this information in and you change that 250 to 500.
Yes.
Because you got to go from the panel and it's got to come back.
Yeah.
That's where you get.
Yeah. Listen. Think about this. Yeah. The ohms that you're dealing with, the resistance and ohms that you're dealing with is the resistance of 200 feet, not the resistance of 100 feet. When you add the ohms up, the ohms are going to be double that of 100 foot. If it's a single phase circuit like this, and most of what you're doing is single phase, isn't it? Most of it is. Now, three phase, you do need to know it. It's not in that chapter, but I put it in. You're going to get it. You got to have it. You got to have it. Because on them farms, even on them farms, you got well pumps and stuff that are 3-phase. You got things that are 3-phase. Even though most of the stuff's not, you still got to have it. The entire building does get 3-phase sent to it, right? That's the whole point. The building does get 3-phase. If there's one thing in there that's got 3-phase loaded all, then that building receives 3-phase power. And you would use the other formula, not this one, for the whole building. If you're doing a calculation for the whole house.
Most of the houses, they get it same thing, but some of them, because they have like a well house or whatever, where a lot of stuff goes through, some of them are 3-phase, and then they just want to send the phase out to the house. You need to know both. You need to know both.
Murphy Family Ventures, I taught them a class, 8-week class, and as we were going through it, I kept picking their brain of what did they have, send me some diagrams, and I was just digging like crazy. And they did show some 3-phase stuff in there. They had some on larger pumps, well pumps. And so I did teach a little bit of 3-phase for them, so anyway. Okay, now, so this information now, so what do we do next? So we're going to do how we figure the voltage at the motor. Well, actually, we're looking for what? We're looking for the wire size. So look, so you put the voltage drop under here, the 4.4 VD, and it's going to give you the circular mills, right? So what does that end up being? Right, 29,318 circular mills. So 29,318 circular mills. Now that number may not be exactly match a particular wire size, but if it doesn't, you've got to go up to the next one above it. You can't go under. It can't be any less circular mills than that. You always have to step it up when it falls between. And most of the time it is going to fall between some numbers. So 29,318, and let's kick back over here. 29,318. Can you use the number 6? Nope. You got to make a big jump and go up to what? Right. You have to go up in those increments, and that's just the way it works. You cannot go smaller. Cannot do it. You would have a very embarrassing situation. They'd look at you like, "Hey, that dude, he don't know what he's doing. We're not going to let him pick the wire size no more." They'll laugh about it. He'll be talking about it 5 years. You know what I mean? When they see you around, that's what people remember. They want to remember what you did wrong, and people love to pick on what you did wrong. Ain't that right? So this is this book is great. But let me tell you a funny story. We had a guy, and you know the guy. You know the guy. He's the guy you replaced. This guy said this. I'm serious, man. I'm not gonna say his name, but you know him. So you replaced him. He said, he looked at the size of this book here. He looked at the size of that little book right there, and he says, "I buy my son coloring books thicker than this little book." He looked at that in the beginning of the class, and he picked at the book and said, "I buy my son coloring books thicker than this." Like he felt like he was getting ripped off. I said, "You wait." I said, "That book is going to unzip like a darn flash drive, and you ain't going to know what to do with yourself when you get into it. It's going to get way bigger than what you think." And it did. Boy, I noticed. He was struggling trying to catch up. To them, it was not. You can't go by the size of something. You really cannot. There's a lot, but I remember him saying that I think the first thing he shook his head. I buy my son coloring books thicker than this book. I thought, I said, "You wait and see, man. You just wait and see." Yeah. Anyway, it was fun. Okay, let's go back. And so you solve that one. Okay. And so now we need to jump on we're going to hit some high spots in the worksheet, because that was the last example in the book. Let's skip over now to over to Moodle, and we're going to open up our worksheet for chapter 9. We're going to get some in there, some things that you haven't looked at. Well, not yet, but yet some on the free page you haven't. So if you go to the welcome mat, you come on down, and you go on down to makeup assignments for November 17 and 19. Now again, our last regular day in here will be November 12 because I got surgery on the 17th. Okay. So you're missing 2 regular class periods in here. So the week of the 17th and 19th, you can use that week to study. Go in Moodle and print. When you open up your worksheets, go to the right side of the screen, hit review. It's going to pull it back up and it's going to be graded. And you can print those. What I would recommend doing is when you hit the print button, print it to a PDF file. Give it a name and save it on your device. Save it on your phone, save it on your laptop, save all of your work, save all of your worksheets after they're graded. And then you've got something to study by. If you save them as a PDF, they can be opened up on your phones and they can be printed on paper. I would recommend doing that, both have them on the phone and also put them on paper. And you've got a physical copy. I mean, I trust electronic devices to a point, but I still would rather have paper and the electronic. I'd rather have both. You know, if your phone happens to fail at the moment, and you're not supposed to be using the phone on the exam for one thing. There'll be a proctor, you know, you'll be using little Chromebooks that are over in the carpentry area, over in the next shop over. There's Chromebooks over there. And that's what you usually do your exam. You have to be on campus to do it during the designated time. You can't do it off campus. That was decided over my head not to allow people off campus to do it. It has to be done here on the Chromebooks. They're small little computers, and they're over in the carpentry area. And I got to find out from him, can they be brought over here, or do you have to go over there? I don't know which way that's going to work. So I'll find that out and let you know up front. But you got actually a little bit over a week study for the exam, so that's good news. You come back in on the 24th, the following week on a Tuesday to do the exam at normal class period time. And that's the only time they're going to allow you to do it. So that's kind of I don't know what's going to happen if somebody can't be here then. Because I won't even be here. I won't even be in Clinton. So if you think you're not going to be able to make it at that time and be here, please say something, and I'll have to get with Barney and find out what kind of provision can be made to make sure that you can do it. Somebody asked about doing it early. They told me it has to be done in the normal class period, is what I've been told. So I apologize about that. If I was here, it could be more flexible, very much more flexible than that. But yeah, 12 o'clock. Do one now. No, because it won't even be written on the 12th. I don't even have the exam written. This is going to be a brand new exam. That's going to be from the beginning out. All the exams in previous years have been the last few chapters. All the previous years, you have about 3 or 4 different tests by now. You've already had at least 3 tests by now. You haven't had any tests in this class. We just haven't been able to do it. I just said there's no time for all of that because we're not going to get the labs done. We're not going to get material covered. With us doing the Zoom and all that, it just changes everything. So I said we'll just do one. Just do one test. And I'm just going to pick a few items out of every chapter that we covered. And it'll grade itself. It's going to be multiple choice, true, false. You have to do some calculations, but bring a regular calculator. Don't count on using that phone. Bring your calculator. And I don't think somebody's going to come. They're not going to come here and give you a calculator. Now, there may be a calculator function on the Chromebook you can pull up. That you probably could do that. But if you can't, I'm sure somebody will say something. They saw you using the phone. People can be sending messages and stuff like that, and that's not allowed to use phones. So make sure you've got your regular calculator. And there'll be a number of them in there to where there'll be some numbers in there. There'll be a problem. You have to solve it, and then pick an answer out of a couple of answers. So you got to calculate the right answer to do. You don't have to show your work, but you just got to pick the right answer. because the exam has to grade itself. It has to be when you're finished, it's done, and it's already that somebody can copy paste it into Web Advisor. So let's go down here. Let's open up the worksheet. Let's do a few of them. So again, make sure that you do Chapter 8. Chapter 8 worksheet. You can download the wire chart. That's physical. That's the paper copy there. You can download the PDF. If you want to go back and review, the recording of Chapter 8 is right there. This is the new worksheet. This is the voltage drop, the formulas that I have here. If you want to have the PDF, download that and save it. So let's open up the worksheet. I'm going to go here to and so here, this is going to be, we've already gone over that in this. Let's just skip the one that's something that we haven't done, okay? Because you've already done that. You're going to go through, you got to do your calculations, you got to pick the right one, see? We don't need to do that one again. We don't need to do that one again. We don't really need to do that one again either. Or that one. Or that one. Now let's back up and do this. Number 7 says, it refers back to number 6, and it says, we're going to change problem 6 so that it's using number 8 wires, but where up here it was actually number 10 wire. Find the voltage at the load. Let's try that and see what we get. Let's see if I can get my drawing. Get the pen function back. Oh, okay. There it is right there. I don't know why I didn't. Take this over there. So the original circuit, you had a 110 volt DC source. Let's actually draw a circuit here. So you got a so you got your voltage source generator, 110 volt DC, 110 volt DC. And you have a load circuit out here. We don't know what load is. I'm just going to say load. Drawing pictures makes it a lot better. And so we're seeing now that it's changed to number 8 wires. So number 8, AWG wires. And the only thing changed was that right there. We're still talking 25 amps. And it's 500 feet away. That's your distance. And so it wants to find the voltage at the load. So voltage at the load will be what? So which formula do we start with? Out of those two formulas, are we searching for what? Yeah, voltage drop, and which would be what? VD is KIL over what? Over CM, yeah. So K, and if you back up, it tells you that the one thing I forgot to put in there, and the K is going to be 12.6 in this case. And I just realized I need to fix that. Hold on, let me fix it now. Because it's not even in there. So if you didn't know that, you ended up using the 12.9, and the answers are based on a 12.6. Let me fix that real quick. You can be doing some figures real quick. Let me doctor this thing up in Moodle here. I just converted this last night into a Moodle format, and I forgot to put the K factor in. So we do that real quick.
There was this 500 foot going to the low.
Mm-hmm.
You still got to come back out of the low.
It does. You got to double that. You got to double that. So let me escape out of this. Let me fix the let me go into edit mode here. So we're on number 7. And look, I'm going to put the K factor in there. Okay. K equals 12.6 in this case. Okay. This is on number 7. K equals 12.6. That's very important because I didn't specify that. Okay. So let's go in and let's go to the preview and make sure everything looks good. Go to number 6. I mean number 7. I'm sorry. See, now I've got the K factor in there now. So that's going to be specified. And I need to go back and see because I actually forgot to put the K factors in these. So number 8 has a K factor of 12.6. Let's go ahead and do that one. Get it? K equals 12.6. I stuck that in there for number 8. Save. Y'all see that? Number 8. And we can go over this. Let's just make sure. Back it up here. Yeah. Number 6, I didn't put it on number 6. I've got to put the K factor in these. I'm sorry about that. So I'm glad nobody's tried it yet, because once you start, then I can't. I can edit stuff like that. Edit question. I go in now, and for number 6, K equals 12.6. 12.6. That's for number 6. K is 12.6. Okay. Save changes. See there? It's right there, 12.6. How about number 4? Is actually K is 12.9 on number 4. Let's go back up to 4. And I didn't include it. It has to be included. I just did this last night. I converted. It takes, man, a buku of time to convert these things, man, the first time. I've never done this class in Moodle. It's the first time. And you've got the copy, paste, and it's just, man, I was up late doing this stuff, man. But all of this boils down to me getting surgery, man, because I pushed my surgery out. The surgeon said I got to have 6 weeks recovery time minimum. So he wanted to do it back in spring. I pushed all the way to the end of the year, give me 6 weeks and back it up, and it lands where I've got it planned. Exactly. With no budget room. And that way I'm not really causing much of a problem with y'all, only missing 2 regular periods. But it needs to get done before I end up paralyzed. It's heading toward a bad thing, it's getting worse. So for number 4, Moogle's actually a great thing since I've gone into it. It's you know, it makes things possible when you enter a pandemic, man. Otherwise, it would be a real mess. It would be, it's already a mess, but this makes it not so much of a mess. So this is number 4. K is 12.9 here. So why are we changing it? So that you can do it in different temperature ratings like reality. In reality, when you go take the state electrical test, whatever they tell you, you've just got to be looking for that K factor because it's not always the same. But in general, if you want to do worst case, 12.9 is worst case. If you want to be on the safe side, doing the installation, I would use 12.9 for that. You know. You could go by the minimum because of the temperature. You could go by the lower one. You could look at the go back in chapter 8 and look at what's the lower one, the lower temperature rating. So number 4 is 12.9. What you take a look at it. Number 4. Right, I've got 12.9 K in there. Okay, so the 10.4 was no, you wouldn't use that. No, I wouldn't use that because listen, man, in a house can easily be hotter than that. You know, I step it on up to there. I would use no less than 12.6. Yeah.
Been running in the attic, it can read it.
Yeah, right. And to be honest with you, I honestly would use 12.9. I just go ahead and use worst case. Go ahead and use worst case, man. I mean, why not? You know, why not? You want to be a reliable on what you calculate, what you buy, what you specify, and you want your work to stand 30, 40 years when you do it, right? Now listen, in your house, whatever years was built, whoever wired that thing, if you ain't had no major problems in there, they did something right, didn't they? They did something right. I mean, you know, house I'm in, thing was wired in 1977. Are you serious?
Yeah.
They didn't run the right number of wires. Oh my gosh. What now? You got to have one of a certain way for the other one to work.
Yeah.
They didn't run a 3-wire cable.
Yeah.
Well, ain't that pretty? Won't that pretty? Wouldn't you be proud of that? Hire somebody like that. And listen, and they didn't fix it. They just went on with somebody. So the inspector missed that.
The electrical inspector passed.
Yeah.
I'll put it to you this way. This is my house.
It's looking.
I'll put it to you this way. My house is so old, I don't think they handle it.
And look, they've had National Electric Code since the late 1800s. In the late 1800s is when the National Electric Code come out because it was up north. The mills, the first factories that were made up north, they had a lot of mill fires up there. The first factories it was created because the people were installing electrical wiring and they didn't know what they were doing. So the National Fire Protection Association, NFPA, they formed a code book. They formed it in the late 1800s. Seriously, they did.
It's either Spectre or some agency actually came out to the house on that,
Yeah. My mother's talking about stuff like that in the good old days.
Yes,
she thinks about like that, man, and it's almost like she would live like that, you know. Okay, now, so let's move forward now. Let's go. Let me make sure I'm saving here. Finish temp. So now let's go on down to, we were on what, number 7? We were on 7, exactly. So we changed it to a number 8 wire, and we're looking at KIL over CM. Okay. So somebody kind of tell me, what do we do next? What's next? Exactly. Exactly. So in this case, we see cable's going to be what? 12.6. So we're doing 12.6. ohms. I like to actually put the symbols in there to show what is that 12.6. It's actually resistance. And then we're going to multiply it by the I, which is what? The current. It could be what? And I'm going to put amps beside that because it stands out and it makes more sense than just a bunch of numbers thrown in there. What are these numbers? It's ohms, it's amps, and then it starts to look like something we've seen, Ohm's law. Ohm's law is actually embedded in this. It's in there. You can't never get away from Ohm's law. George Simon Ohm, he was a German physicist that came up with this. You can look him up. And people, his peers didn't really accept his theories right away. It was a ways on down the road before they really accepted and realized that he knew he was exactly right back in 1800. You look him up, George Simon Ohm. All of these terms like voltage, volts was named after a French, I think it's a French physicist. His last name is Voltaire. The amps was named after a French guy named Ampere. His last name was Ampere. They're all of them, or that I know of, were physicists that were European physicists. So L is going to be what? 1,000 feet, because it's a round trip. You've got to double up on the resistance there, because you are traveling 1,000 feet with ohms there. And then CM for a number 8 wire is 16,510. And where did you get that at? He got that off of a chart in what chapter? Chapter 8. I'm not going to flip back to it. Y'all go back to chapter 8. You're going to find it there for number 8 wire. It's going to be the 3rd column. It's going to give you that. It's an exact number. Okay, so what is the answer? How much? Okay, what's around the 19.08? 19.08 volts. And that's going to be your voltage drop, right? So what would be the voltage at the load if you're going to lose 19 volts? And that's a lot of voltage that you're losing in. That's not a good thing. That's bad. This is not a good setup. This would not be acceptable. This just to show you this is a bad deal here. This ain't what you want. No more than 3%. The National Electric Code says no more than 3% for a single branch circuit. Now, let's say, for instance, I need to get this document to show it to you. I've got it. I just need to get a copy of it and get it to all of y'all quick. Here's your rule for National Electric Code. If you're going from the highway out to a hog house, and then you go from the hog house to a fan in the hog house, your total voltage drop from the highway out to the fan that you're going to can't be no more than 5%, a total of 5%. If you figure, say, 3% from the highway to the hog house, you ain't got but another 2% you can go total when you figure the total run. But you always want to start out your best off just figuring on a flat 3%, But they do allow a total of 5 whenever you go from a source to a building, and then within the building to a load, you can have a total of 5%. but no more than that, because then your fans are going to start, they're going to be grown and running on low voltage. They're going to be running high, burning things up. You're going to lose equipment. Stuff ain't going to run good. Okay? So what's our voltage at the load? 90.92. So that motor's not going to be happy with whatever it is. That load's not going to be happy, not when it's looking for 110, you know, it's not going to be happy. But what you can do, you can actually use the other formula that says CM equals what? And it's going to crank out and give you the right thing, right? If you wanted to do that. It's not required in here to do it, but if you were going to do that, you would simply use the other formula that says CM equals what? Over VD. So here's what you would do. You would say for VD, you know, you would put the same numbers in here. For VD, you would say 3% of this. 3% of this and plug it in, and it's going to give you the circuit of mills, and you go to the chart in chapter 8, and it's going to give you the wire size for 3%. If you wanted to do it, it wouldn't hurt to go ahead and do it. I think you know, if you want to take a second to do it, what would that be? It would be the same KIL. And then what's 3% of 110? Times 0.03. How much? 3.3 volts. So now let's plug in the number here. The same things there, and do this divided by 3.3. And then it's going to give us the circuit of mills, and we'll go take a piece of wire. I haven't figured that. I'm going to just go off of what you're telling me. What'd you get? 95,000 what? 454.55 cm. 95,454.55 cm. Let's go to the wire chart and find out what that is. 95,454. $95,454 is going to put you where? A 1-aught. A 1-aught. Now, 1-aught, 2-aught, 3-aught, 4-aught. A 1 AWG is a particular size. When you go 1/0, you pronounce that 1-aught, 2-aught, 3-aught, 4-aught. That's a different set of numbers, and they're bigger. So look, you're going from what was the original figure there? It was we were using number 8, right? We were using number 8. The actual correct wire size would have to be a 1-aught, way bigger, way bigger. You see that? Whole lot bigger wire. And this is the real ticket here. This is how you find out the right size wire to use. That and a lot of folks don't know this stuff, even though it's not hard. None of this stuff is hard. All you guys got to know how to do is you got to have exposure to the formulas, the information, and you just need to see it and do it, and it's simple as pie. And every one of you really should pursue all the electrical you can in your lifetime. At some point, you should pursue getting an electrical license, state license. You should pursue everything you can get. Don't miss nothing in the electrical field that you can take, because every one of you's got a high aptitude for this. If you didn't, you wouldn't even be in the room. You're proving by being in the room, you've got a great aptitude for it. You have a want to, and I didn't know for a fact every one of you can ace all of this stuff. And a lot of you listen the same way. You wouldn't be listening on YouTube if you weren't interested. You wouldn't go this far if you weren't pretty good at it. So I say, stick with it, keep learning Take everything you can get here just in the electrical field on this campus and keep going, keep going. And don't forget my fish plate one of these days. When you get a raised fish plate, please. I'm just kidding here. All right, everybody good there?
No,
Uh-huh.
put that screen back to where it was. I had to
Mhm.
So we got 3.3 volts.
We said that the 3% of that would be the 3.3. Is that right? Now I didn't figure it. Now I just know that's what code is. I didn't do the figures here now. 110 volt times that. Listen, what you're doing is you're saying that you're not going to. Now what's the voltage at the load now? So what's 110 volt minus 3.3? Let's figure that. 106.7 volts. So look, your new figure is going to be 106.7 volts. This is the correct number at 3%. This meets the electric code right here. It meets electric code at 3%. That motor, that load will be happy at 106 volts. It'll be a happy camper, okay? It's like you having a full belly, okay? You'll be a happy camper. It has a full belly at 106 volts, okay? Here at 90.92, it's not happy. It says I'm still hungry. I don't have enough voltage here. Not happy. The motor's going to moan and groan. It's going to go wah, wah, wah. It's not going to be, it's not going to be happy at all. Matter of fact, it's probably going to overheat the motor. Motor probably it's going to die premature if you keep running it that way. It's not a good thing. Yeah. But I'm telling you, this formula, this is the one that you need to always remember that is very straightforward, very exact. It's an engineering level thing. You use this on state electrical tests. All contractors have to use this stuff. If they're going to do reliable installs, they use this stuff, okay? Everybody cool? Okay, any questions? Let's click on to another one. We got to cover 3-phase. We got to cover that. You got the circlet here with your thing. Well, all right. It's funny how these smart boards are. You go in a different room, there's some different rev level on software, and the features are different. It's funny how that is. Now, number 8, it says, determine the copper conductors necessary to supply a parallel group of 5 lamps in a 300 watts each. So let's draw the circuit. If you draw the circuit, it's going to be much simpler. You're less likely to make a mistake. So you have and the voltage is 120 volt. Actually, look, we got 3 phases is the next one, and we can still work that in. How many of you can stay to say 2 o'clock? If you got to go at 10 till, you have to go at 10 till. It's where? Right across the hall. Okay, what we can do, look, let me just tell you in a nutshell what to do with this one here. So we can click on, there's 2 problems on 3-phase we got to cover. We have got to. Here you got 5 lamps to the 300 watt each. You're gonna have to do what to get a total wattage? When you go to figure the I in there, you know, you're looking at what's the you want to know the size of the conductors, right? So you're going to be doing CM, right? CM, KIL, VD. Now look, the I in here, you got to get the I based on wattage and based on volts here. You got 120 volts, 5 lamps, 300 watts a piece, right? You got to use the watts and the volts. Get you a total wattage there with 5 lamps to the 300 a piece. And the 120 volt, you got to use Ohm's law and calculate the current in amps. Okay, you follow that? You know how to do that, right? That'll give you the I. The rest of it is self-explanatory. Everybody cool? Look, you say 5 times 300 is how many watts? 1,500 watts. And you have for P, and you have power in watts, you have volts, and you have amps, right? So look, when you're dealing with the power in watts, it's going to be what, the 1,500? 1,500 watts, and you have 120 volts. You cover up I, and it's going to be what? What's the formula for I? 1,500 over, right, will give you the current in amps. That's how you figure the amps. You got to divide, say this divided by 120 will give you I. You plug the I in, and the rest of it you already know how to do, right? Everybody cool? Okay, now, so let's move on. That way, because I don't want to run over, and you end up, we got to cover 3 phases, and I can't leave anybody out of that. Cannot, will not. So here, we got a different animal here. Different animal, watch close. For 3-phase circuits, you have 3 hot wires going out to the motor through a motor starter. If those of you that haven't had motor controls, this will be new to you. So you have the power source has 3 hot legs, and there's also a ground involved out here. But 3 hot legs, not 2, but 3. 3-phase power. It goes through a contactor with 3 contacts in there that closes the overload into the motor. So we're focused on the motor itself, and you have 240 volt 3-phase here. You have a length of 350 feet from the motor starter to the motor, and it's that's the voltage and the amps and the distance. So the question would be this. What in the K factor is 12.9. What is the acceptable voltage drop at 3%? Now that's very simple. You know, you're starting out with 240 volt, right? So 240 volt times 3% would be what? 0.03, right? And so what is that? And I've even spelled that out for you. See that? What? 7.2. 7.2 volts. So that's very simple. That you're allowed to have 7.2 volts and no more than that to be with electric code. Okay. Obviously, I can put the formula in there. I will make it as clear as possible. Okay, because this is not included in the book, but you've got to have it. You've got to have this. Now, these are the formulas here for calculating voltage drop and conductor size for 3-phase circuits. And, you know, you didn't have to use that in this problem, but you will on the next one. The next one's going to be using this. So the next one says, based on number 9, answer the following. What's the minimum size wire that can be used for this motor? you want to be able to use the formula down here for CSA, that one right there, use that formula. And here, the 1.732 is a square root of 3. That's what you have to use. Instead of doubling the length, you're going to take the exact length, the distance, and you're going to put this figure in there. And that's going to take the place of doubling the wire size, doubling the wire length. It's going to be this because it's 3-phase. I can't explain to you the roots of it. I just know the engineer says that's what it is. That figure is going to come up when you go measuring voltage. I can tell you about that 1.732. If you go here, listen good here. If I measure from phase to phase with a voltmeter, it's going to read 240 or 240 or 240 between any two of them. If I read from phase to ground, hold on a minute. Let's don't even go there right now because let's don't go there right now. It's not time for that yet. Not time for that yet. Let's go on. Not time for that. So this question here says, what is the minimum size wire? What is the minimum size wire? And we know that we were allowed a voltage drop to 7.2 volts, and we want the wire size. So what is the formula here? What formula do we use now to get wire size? CM equals KIL. Well, actually, look, it's more to it than that, isn't it? We have to use the we got to use this one here, 1.732, which is square root of 3, and then KIL times KIL.
So you have to add that extra number there on 3.
You do. That's the bottom line. That is the bottom line. That's it. That's what the difference is. So 1.732 times the K factor, which would be, what was the K factor that I gave you earlier? 12.9, wasn't it? Or 12.9. 12.9. This is the problem. Times 12.9. And then we're also looking for the current. I will be the current. We got the K, and then I would be what? What was the current that we had in above the problem? It was 54 amps. You go back up in problem number 9. $54 amps. 54 amps. There, that's your current. And then then you had 350 feet, and you got to do what to that? Nothing. Listen, the 350, you leave it alone because you're putting this in there. This takes place of doubling it or tripling it, okay? You put the straight 350 in there, you don't alter that. Okay. And then under the 350, you put you put VD. And the VD was the 7.2. And then what do you end up with? This is the proper way for three-phase. And don't round no numbers. Just give it exact. It's going to give you the circuit on mills. It's going to be a pretty big number. 58,000 what? 649 and 85 CM. Now, if you're getting something different, then something's wrong. You need to refigure it, slow down, and refigure it. Does everybody agree with what we just had right there? Now, are you ready now? Let's flip over and find the wire size based on, now look, the point, you got to multiply all them numbers up there and take the answer divided by 7.2. 7.2, 7.2, yeah. Now, so look, 58,649, y'all, everybody agree with that? Let's flick over and let's find the right size wire for this. So can we use a number 3? Why? What listen, I'm gonna just give you a funny response. The boss man in person says, look, we don't have enough money to buy that big wire. Why can't you use a smaller wire? I mean, if somebody says something stupid like that, and they say, look, we're running low on money this month, and we can't, why can't you get by with something that why can't you use that roll of wire? You know, we've already got a roll of wire over there, you know, this size. Why can't you use that? And they're just, you know, not that they would. So what do you tell them? What do you tell them? You tell them it ain't going to work. You tell them it's not going to work, you have to buy a wire twice. It's going to cost them double. You won't buy a wire one time, you buy a wire 2 times, probably have some bad fan motors and a lot of downtime and some sweaty hogs, probably some dead sick hogs, and you might end up losing the whole darn farm of hogs because of the, you know, I'm being funny here, you know. Curtains would drop, you'd have a mess. You would have a royal mess. So what size wire are we going to use? Which size wire is it? You're dealing with 58,649, so you got to step it up. You got to step it up. Those are the increments, and that's it. Any questions? How do y'all feel about what we covered today? Lost his hope and goat. Last year's Easter egg. Huh? Good. Alan Strickland will say, I feel as lost as a fly ball in high grass, you know. Yeah. Clear as mud, right? No, it should be nice and clear. Y'all done very good, thank you, and I'm proud of you guys for doing as well as you're doing. My reward basically is to see you guys use this stuff to do it, and when this semester ends, I have a sense of satisfaction when I see people doing it, using it. That's the whole. That's the reward for being in this, other than a paycheck, good paycheck, and some benefits, you know. So it really is. I'm thank y'all for what you're doing. It's a pleasure to work with you, to see you learn and to keep going. You come on back in January, keep learning, and we got plenty to show you. I won't never run out of something I can show you because I've been in this thing 36 years, and we ain't got enough time for me to show you everything no way. Okay, I'll try though. Yep. Okay, so here we go. Whoever may be watching the recording, thank you for watching. You can contact me if you got questions. For those of the class, you've got my number. And if anybody else happens to be watching, you can drop me an email at dking@samsoncc.edu. Be glad to help you. I'd like to get you enrolled in some classes out here at the college to learn more electrical and to get your skill set up from where it may be. And I thank y'all, and you have a blessed evening, and thanks for watching. We'll see you later.